start now. So welcome to the second talk of the evening session. It's a great pleasure to welcome Professor Neal Koblitz. I think we all know him through one or more of his beautiful books, and his books made our graduate student life very pleasant and inspiring. Today, he will tell us what happens when the values of pure math get refracted in applied math for better or worse.
Thank you. I'm very pleased to be speaking at this conference in honor of my friend and colleague of many years, Balasubramanian. So I'll talk about both the good and the bad side of how values of logic and rigor get imported into applied mathematics. I'll start with some positive examples and then talk about the misunderstandings and foolishness that sometimes occurs. But first, before I discuss get into the mathematics, I want to give some memories of a wonderful 2-month visit that I had at Math Sciences in Chennai in January and February of 1987, hosted by Balu. So after talking about some of my fond memories of that time, I'll move on to talk about a joint result with Balu that we published somewhat later. And then a result that helps in some practical questions in elliptic cryptography. Then I'll talk about an example. I'll talk briefly about an example that goes in the other direction in the sense that it shows how practical questions in cryptography can sometimes motivate interesting theoretical work, in this case, in analytic number theory. Then I'll move on to sort of the negative side of my talk, where I'll talk about logical flaws that arise sometimes in applied mathematics. I'll give the example of a misapplication of the uniform boundedness theorem of Osterley, and I'll talk a little bit about non-uniform algorithms. So to begin with some memories from 1987, I gave a series of talks on cryptography. And in the first talk, which was an elementary talk, I wanted to give just a simple example of decryption. And since I was in Chennai, I thought it would be nice to do this in the Tamil alphabet. Well, I only know one word in Tamil, which is Chennai. So I decided that that would be my plain text example. In other words, when you decrypt the ciphertext, you get a plain text, an ordinary word. So this is my plan, but I soon learned that the Tamil alphabet has something like 250 letters. So to give an example in that large an alphabet would be time consuming and cumbersome. And so I felt I should simplify things. So I looked at a table of the Tamil alphabet and saw that there are 30 letters that are either pure consonants or pure vowels, the 18 consonants down the first column and the 12 vowels at the top. And then I saw that the reason why the alphabet was so large is that a single letter is normally used to represent both the consonant and the following vowel sound. So I thought, well, maybe I can just use the 30 letters of pure consonants and pure vowels. So what I did was I looked at Chennai, which is in the upper left-hand corner here, and I saw the middle letter is a pure consonant, the N sound. There are only 3 letters. The letter to the left of that's the letter with the dot on top, and then the letter to the left is the CHE sound, and the letter to the right is the NAI sound. So I just thought, well, why don't we turn that 3-letter word into a 5-letter word by breaking up the letter to the left into the concatenation of a pure consonant for the CH and a pure vowel for the E. So I did this. I gave my example, and the ciphertext was written in this 30-letter simplified alphabet, and then the plain text that came out of the decryption was this nice Tamil word Chennai, except everybody looked at it and scratched their heads and didn't know what I was doing, what this was supposed to be, these 5 letters. And so I learned the hard way that, in fact, in Tamil, nobody would think of this sequence of 5 letters as representing anything. And you can't simply transform letters this way. So my attempt to give a simple decryption example in Tamil was a bit of a failure. So, well, after that, I think things picked up in my lectures. But I learned my lesson not to try to give an example in Tamil ever again. Okay, another memory I have is from visiting the Indian Institute of Technology right next door to Math Sciences to talk about Vietnam. Now, I'd just come from Vietnam, where I was heavily involved in trying to foster scientific cooperation with Vietnam, to break down the isolation that Vietnam was under at that time, its lack of contact with countries, with Western countries and other Asian countries. So I was, at any opportunity in India, I was talking about this. And in fact, I felt strongly that there should be much more South-South cooperation between India and Vietnam. And so I was talking a lot about this. And then I met some faculty from IIT from next door who came over to Math Sciences to attend seminars and talk to people. And they invited me to give a talk on a little bit on the history of Vietnam, which their students didn't know anything about. They were quite concerned because they felt that many of their students had a type of mindless veneration of the United States. You know, someone from the American consulate in Chennai had visited recently and been received with open arms by the students who didn't ask any hard questions. And so these faculty members wanted me to come and provide some balance, that is, to talk a little bit about the negative side of America's role in the world, of which Vietnam is a prime example. And so I talked about the history of Vietnam and about science and mathematics in Vietnam, and had a very nice visit to IIT. In connection with that, some graduate students at Math Sciences who were from Kerala belonged to a Science for the People organization and requested that I write an article about science in Vietnam for the magazine, the publication of their organization, which they translated into Malayalam and sent me a translation. I was very proud of this translation. Having written an article that was translated into Malayalam was very unusual. Another memory from those 2 months was going with Balu and some other people to a concert of traditional Indian music, which lasted around 3 hours without any break. Now, Americans are not used to sitting still for 3 hours, especially on a hard surface. So maybe toward the end of that, it was a little bit uncomfortable, but still, it was a beautiful experience, and I really enjoyed the concert. Then a strange memory, a strange thing we did was Balu and I went to see the dreadful American movie Rambo. Now, why did we do something like that? Well, one of the things I was going around talking about, I was complaining that it was disappointing that the movie Rambo was showing in India to full houses at that time, because it's an absolutely awful movie. It glorifies violence, it glorifies American aggression and militarism. It has racist portrayals of the Vietnamese people. And I was going around saying, well, why would India even show a movie like this? India, as I said, has a whole history, very good relations with Vietnam. And in fact, India and Vietnam share a common legacy in the 20th century of bringing imperialism to its knees. British imperialism in the case of India, and French and American imperialism in the case of Vietnam. So I didn't see why such a movie would be shown in India. Well, my Indian friends explained to me that, well, people who go to see this movie don't care about the history or the politics of all this. They're just going to see it because it's entertaining, there's a lot of violence, special effects, adventures, and that's all that matters. So we were talking about this, and Balu and I decided as an experiment to go sit through the movie, and then after the movie, as people left, we would ask them about why they saw it, what they thought about it, and so on. Actually, Balu would ask them because I don't know Tamil, so Balu would have to do the questioning. Well, as it turned out, this experiment was not very successful. The people leaving the movie were not eager to be interviewed about it. They were not eager to talk to Balu about their impressions. Nobody wanted to say anything. And so it was a failure as an experiment because it had a cost. The cost was that Balu and I had to sit through this movie. So in a way, it was an entertaining experience to go through all this, but we did not really learn anything about what people were thinking when they were watching this movie. And the final memory I want to share is I was jogging in those days and would jog at around 6 a.m. before the heat before the heat became too much for jogging. And at around 6 a.m., the sun was rising and it looked like this. And I don't think there's a more beautiful running route anywhere in the world than the shore by the Bay of Bengal at 6 o'clock in the morning when you see the sunrise. So it was a wonderful memory of jogging in Chennai in 1987. Okay, so now to proceed to the mathematical part of my talk. Some years later, in 1995, I again visited math sciences in Chennai briefly, and then several of us, Balu and I and some others from math sciences, went to a conference in Bangalore at the Indian Institute of Science on the subject of cryptography and computation. It was organized by Balu and Benny Madhavan, and I gave a talk there on elliptic curve cryptography. Well, in elliptic curve cryptography, we want an elliptic curve E defined over a prime field Fp that ideally has a prime number of points, say Q points on it. It doesn't actually have to have a prime number of points. For purposes of cryptographic applications, it's sufficient if the group order is a very large prime times a small cofactor, like for example, twice a prime. And here, the order of the group has to belong to the Hasse interval of length 4 root p centered at p plus 1. There's another condition we also need for security, so that our crypto system is secure. Namely, we don't want the elliptic curve group to embed in the multiplicative group of a small degree extension of the finite field. That is Fp to the k for k less than log squared p. In other words, we don't want this prime number of points q to divide p to the k minus 1, that is the order of the multiplicative group of that extension. We don't want that divisibility for small k. So we have two basic conditions for our elliptic curve over the prime field, that it have a prime number of points and that it does not have this divisibility. In my talk, I said that heuristically, it seems very practical to find such curves, but just using a randomized algorithm. But I thought it would be hard to prove a rigorous result guaranteeing the probability of randomly getting such a pair consisting of a prime and an elliptic curve over the corresponding prime field with the desired properties. So that was what I suggested, that this would just be very difficult to prove this sort of thing. But right after my talk, in real time, Balu said he'd come up with an outline of a proof that could give exactly the result that I wanted. And this eventually led to a joint paper published 3 years later in the Journal of Cryptology. So here's the main theorem in that paper. Suppose we choose random pairs P comma E consisting of a prime and an elliptic curve defined over the corresponding prime field having a prime number of points, where the prime P is between m over 2 and m. And here, in practice, m would have to be very large in cryptography. M would have to be roughly of order 2 to the 250th power. So m is a very, very large number. Then the probability that that when we choose this random pair, we'll have the divisibility property that we don't want, namely the order, the point order, the order of the points q divides p to the k minus 1 for some k less than log squared p. That probability is less than an effectively computable constant times log to the 9th m times log squared m divided by m. And in view of the magnitude of m we'd be dealing with, this is a negligible probability. Okay, just some background on this. Note that if you fix p, if instead of varying both p and e, if you choose your favorite p of the right magnitude, and then just choose variable elliptic curves, then nothing can be said about the probability that a random elliptic curve over that fixed prime field has a prime number of points, let alone anything about the divisibility property. And that's because you need to know information about primes in an interval of size 4 root x. However, if you regard both p and e as varying simultaneously and choose a random pair, then you can prove that that p is prime and a random elliptic curve over fp has prime order roughly as often as heuristics would say. The order of the elliptic curve is very roughly uniformly distributed in the Hasse interval. Not really. It's less likely to be at the ends of the Hasse interval than at the middle, but you get a pretty good approximation, assuming that it's more or less randomly distributed in an interval a little bit shrunk from the Hasse interval. And so you're basically varying two numbers and asking for both of them to be prime. So it turns out that you can get something close to what heuristics would say. And then after doing that, it remains to prove an upper bound on how often, as p and e vary, you get the divisibility property you don't want. So, so that was generally how the proof proceeded. Now, in this case, rigorous mathematics was useful in practical application, useful in elliptic curve cryptography. Well, why is it useful to have a rigorously proved result of this sort? Well, a randomized algorithm, what we want to know is that it's feasible. It's a polynomial time algorithm what we want to know is that the probability that our algorithm does not give us the information we want, namely this pair p comma e with the desired properties, that probability decreases exponentially as a function of the number of iterations of our randomized algorithm. So we'd like to know, for all practical purposes, if we just repeat it 10 or 20 times, we're virtually certain to get what we want. Before this is proved, we can say that we're virtually certain that it has this feasibility property, but that's modulo a conjecture that nobody knows how to prove. So it's much more desirable to be able to say we know with absolute certainty that it has this feasibility property. So that's the type of usefulness of having a rigorously proved result rather than some heuristics. Okay, in some cases we have the reverse influence between applied and theoretical mathematics, where a practical question motivates people to investigate a theoretical issue that they hadn't thought about before. So I want to give an example of that. Before elliptic curve cryptography, no one asked about the distribution of elliptic curves with prime group order. As I said, in elliptic curve cryptography, we're a little bit more flexible than that. It's okay to have the group order to be either prime or a prime times a small factor. Then we can still we can still construct efficient and secure crypto systems. Well, interestingly, the analogous question about the multiplicative group of a prime field, the closely analogous question, was of great interest to mathematicians historically. The analogous question about the multiplicative group of fp asks about the distribution of p such that the group order is twice a prime. That is, p minus 1 over 2 is prime. And that's the Sophie-Germain prime question, because then p minus 1 over 2 is a Sophie-Germain prime, which of course is great interest in the history of Fermat's last theorem ever since Sophie-Germain proved the first case of Fermat's last theorem for Sophie-Germain prime exponents. So it's kind of interesting that it would have been natural to ask the same question about elliptic curves, or the analogous question about elliptic curves, but nobody did it until there was a practical reason for caring about that. Well, the result I'm thinking of, the work I'm thinking of, is by Kumar Murthy and a co-author, Ali Murray, who wrote a paper, an application of sieve methods to elliptic curves, that appeared 20 years ago in the proceedings of IndoCrypt, the cryptography conference in India. And they proved the following theorem. Now they suppose that you were interested in generating elliptic curves a little bit differently than what I described before. Instead of letting P and E vary randomly at the same time, they said, let's suppose that E is a fixed global elliptic curve, that is an elliptic curve defined over the rational numbers. And then we can get, for different P's in the range we're interested in, we can get different possibilities for an elliptic curve over FP by reducing E modulo P. Then let n sub p denote the group order of the reduction mod p, that is the elliptic curve over fp. They prove, assuming the generalized Riemann hypothesis, if the elliptic curve over the rationals E is not a complex multiplication curve, then for at least x over log squared x primes less than x, the mod p group order, is the group order of the curve over fp, has at most 16 prime divisors. Now that's in the direction of what we want. That is, we'd like it to have just one prime divisor, or a prime divisor times maybe a few very small primes. This doesn't give us that. And for that reason, it's not of great practical interest. Or you could use it to construct a crypto system, but the problem is that you'd have to know that the largest prime divisor is at least 2 to the 250th. So for that, you'd have to be looking at if you want to be certain using this theorem that you can efficiently find a curve in this way that has its largest prime divisor at least 2 to the 250th, you'd have to choose P to be at least 2 to the 4,000, because the largest prime divisor might have bit length just 1/16th of the bit length of P. So that could be done, but it would be a relatively inefficient crypto system. It would never be done in practice simply because it would take longer to do everything when you were working with primes that large. So in practice, we wouldn't do this, but it's in the right direction for a rigorous theorem of this form that would be used in practice. But my point in talking about this theorem and praising this theorem is not that it was something that was essential for practice, but it's a very nice result that illustrates that cryptography can have some value in motivating research into new questions in theoretical mathematics. Okay, a lot of work in cryptography relies on heuristic assumptions and empirical experimental work, and is not at all rigorous. But still, notions of rigor and formal logic, when they can be brought in carefully, can be of great value. On the other hand, sometimes notions of rigor and formal logic are brought in to cryptography in papers that make claims about the relevance to cryptography to bad effect. That is, sometimes some rather foolish things are done. So I want to give a couple examples. First of all, a paper also about 20 years ago, written by Cheng and Uchiyama with the title Non-Uniform Polynomial Time Algorithm to Solve Decisional Diffie-Hellman Problem in Finite Fields Under Conjecture. So let me explain what these words mean. The decisional Diffie-Hellman problem, the Diffie-Hellman problem is a basic problem in cryptography. The decisional problem means it's a yes or no question. And the question is the following. the decisional Diffie-Hellman problem in a prime field FP asks, given a generator G of the multiplicative group and three elements A, B, C, is the index of C to the base G, to the base of our generator, equal to the product of the indices of A and B, where of course the index means an integer modulo P minus 1. So it asks, yes or no, is the index of C equal to the product of the indices of A and B? It turns out that that in certain types of cryptographic protocols, cryptographic setups, you want to know that this is a difficult problem. That is, if you choose P large enough, you can be confident that someone who's trying to attack your cryptography will not be able to solve this problem. It's a difficult problem to solve. That's what you want to know in certain situations. So what they suggested, they said they have a certain type of algorithm to solve this problem in polynomial time. Well, their algorithm is a non-uniform algorithm and it requires a conjecture. So I want to say what that means. Well, non-uniform means that when it's a topic it's a concept in theoretical computer science. It means that when you're solving the problem, you're allowed an advice string that's of polynomial size, that is, its bit length is a fixed polynomial, is bounded by a fixed polynomial function of the input length. So a reasonable size advice string that will help your algorithm solve the problem. And when you say a polynomial time non-uniform algorithm, the running time of the algorithm does not take any account of how long it might take someone in practice to find this advice string. So the advice string you just suppose you somehow have. Well, strictly speaking, the advice string has to depend only on the input length. That's not true in the Cheng and Uchiyama paper. They're using uniform in a much looser and precise sense because their advice string depends on P, not just on the input length of P. So if P has 250 bits, the advice string doesn't just depend on that, it depends on what the actual value of P is. However, it does not depend on the other input to the problem. That is, the advice string does not depend on G, A, B, or C. So it's still, it's not a trivial statement at all. Okay, so what is their conjecture and what is the advice string? Their conjecture is that there always exists an advice string of the form that they need. So this is their advice string. And let's suppose, for simplicity, that the order of the multiplicative group of the prime field is twice the Sophie Germain prime. Then their advice string in that case is an elliptic curve defined over a number field K having points of order Q also defined over K. Now, since the advice string has to be a reasonable size, that means that the number field has to be a reasonable size. It has to be describable, and the coordinate of the point of a generating point has to be describable in a polynomial number of bits. So the advice string is the description of the number field and the elliptic curve and the point of order Q. That's the advice string. Their conjecture is that such an advice string always exists. They don't have an algorithm to find it, of course, and you don't, in a non-uniform algorithm, you don't worry about that. You just assume that somehow you have this curve. But the curve has to exist, otherwise you don't have an advice string. Okay, so they conjecture that such an advice string of polynomial size in the bit length of P always exists. The author's justification for this conjecture is the uniform boundedness theorem proved by Oesterle, which says that if D is a degree of a number field K, and if E is an elliptic curve over K with a point of prime order Q, then Q satisfies an exponential bound, essentially 3 to the D power. It has an exponential upper bound. This is what the authors say in their paper. Fortunately, the current research seems to indicate the maximum possible value of Q, that's what they mean by the number of torsions, over a number field grows exponentially with the degree of the number field. Well, this statement is a bit confused. They're confusing an upper bound with an optimal upper bound, which in this case is quite a different thing. Well, it's certainly true that researchers could not prove a better result than Oesterle's result. They could not prove a sub-exponential bound on Q. But it's also true that no family of elliptic curves was known for which Q grows faster than root D. And it was conjectured that Q satisfies a polynomial bound in D. So it was widely believed that Q is bounded from above by some polynomial in D, although nobody could prove that. So the authors seem to think that the inability to prove that something doesn't exist is good evidence that it does exist. So if you don't have a definitive proof that something doesn't exist, you might as well come up with a non-uniform algorithm that uses as its advice string the thing that they can't prove doesn't exist. So analogously in the real world, we might say that we don't have probes to go to the moons of Jupiter yet, to explore the moons of Jupiter. So we might as well conjecture that there are little green men walking across the ice fields of Ganymede. Why not if we can't prove that it's false? So I think few mathematicians would do this, would conjecture, for example, would make the logical leap of conjecturing that, for example, the existence of a non-trivial zero of the Riemann zeta function off the critical line, justifying the conjecture on the basis that nobody's yet proved the Riemann hypothesis. So, their argument that they thought was a strong argument for their conjecture is actually not very sensible. And concretely, one way to think of their conjecture, the elliptic curve whose existence they conjecture we can always count on, is to look at the modular curve x1 of q. Now, the modular curve x1 of q parameterizes pairs consisting of an elliptic curve E along with a point of order q. And in our case, both the elliptic curve and the point of order q have to be defined over a number field k, which means that the point on the modular curve has coordinates in k. So if the point on the modular curve has coordinates in k, then E and q are what we want. But remember that that q has to be very large. And in fact, the type of cryptosystems that are based on the decisional Diffie-Hellman problem require q to have at least 1,000 bits. So the prime order q must be at least around 2 to the 1,000th power. And the modular curve has genus of order q squared. So in a secure cryptosystem, we'd be talking about a modular curve with genus roughly 2 to the 2,000th power. And so we'd have the conjecture is that that there exists a manageably sized point on a Riemann surface that has about 2 to the 2,000 handles. So does this have any value in cryptography? I don't think so. And even if there is such a curve, such a point on the modular curve, at the very least, you'd need divine intervention to find it. So non-uniform algorithms, although they're an interesting, an important concept in theoretical computer science, from a practical standpoint, a non-uniform algorithm is not really an algorithm in the real world sense of the word algorithm, because it relies on an advice string that nobody knows how to find. Well, my co-author, Alfred Menezes, and I wrote a paper with the title Another Look at Non-Uniformity, where we criticize misconceptions about non-uniformity that are widespread among cryptographic researchers, including some of the top cryptographic researchers. So I want to give an example of another type of misimpression about logic and mathematics. Okay, now a typical theorem in cryptography, a so-called provable security theorem, would have might have the following form. And I'll explain what these words mean. If f is a collision-free hash function, then our authentication code constructed from f cannot be broken. So what does this mean? Well, a hash function is a function of messages. The input is a message and the output is, a message can be of arbitrary length, an arbitrary bit string of any length, but the hash value of it, the result of applying the function, will be a bit string of fixed length, usually 128 bits. And it's like a fingerprint of a person. It's a digital fingerprint of the message. The hash functions are used throughout cryptography. They're used in digital signatures, authentication codes, encryption, many other things. The crucial property that you want a hash function to have is this collision-free property, which means the following. It is not feasible to find two distinct x's, x and x prime, that have the same hash value. So it's a type of one-to-one condition. But it's one-to-one in the sense of practical computation, not in the mathematical sense of one-to-one. In fact, a hash function is infinity to one because there are infinitely many messages possible if you don't restrict the length of a message, and only finitely many hash values. So there are infinitely many messages that might give us the same f of x. But the point is that you'd never, in practice, be able to find x and x prime such that f of x equals to f of x prime in a reasonable length of time. There's no reasonably efficient algorithm to do that. It's just an impractical task to try to find two messages with the same hash value. If the hash function does not have this property, then it's not a good hash function. So you always want to assume at least that the hash function is collision-free. Okay, then the authentication code. Well, what's an authentication code? That's a protocol, meaning just a sequence of steps by various parties to the communication. So typically we call two people who are communicating Alice and Bob. So in this situation, an authentication code would be a method in the communication between Alice and Bob, whereby Alice becomes convinced that she really is communicating with Bob and not with an imposter. So it authenticates that it really is Bob at the other end. Okay. Now, the theorem, this type of theorem is a conditional theorem in a very strong sense because it doesn't assume like the Riemann hypothesis, which just about everybody believes is true. It assumes something that might be true now, but maybe won't be true in 10 years. Namely, it assumes that, that nobody's able to come up with an efficient algorithm to find F collisions. That is, your particular hash function, there's no way to just somehow find two bit strings that will produce the same result. It might be a very plausible assumption, but it's still a very strong assumption. The conclusion is also strong. It says that no one can develop an efficient algorithm to break the code, which in this case means no one can imposter somebody else and falsely convince Alice that they're Bob. So it has a strong assumption and a strong conclusion. Generally, proofs of security have this form. They're theorems of the form P implies Q. They're conditional theorems, where P is the assumption that the attacker cannot feasibly complete a certain computational task, such as factoring a large integer if you're using the RSA crypto system, or finding a hash function collision if you're using a system that needs a good hash function. And Q is the conclusion that the same attacker won't be able to break our crypto system by whatever we consider to be the type of break of the crypto system we're concerned about. Access to a restricted resource that they're not supposed to have, retrieving a secret key, being an imposter, falsely convincing Alice that they're Bob, this type of thing. That's the conclusion, that they won't be able to do that. Okay, so my example of a very unfortunate attempt to apply logic to cryptography comes from notes for a course at MIT given by two top cryptographic researchers, Mihir Bellari, who has a phenomenally high H number. He's probably the most cited researcher in all of cryptography, and Shafi Goldwasser, who won the Turing Award, which is sometimes called the Nobel Prize of Computer Science. So this is what they wrote for their students. They wrote, clearly, the non-uniform adversary is stronger than the uniform one. Thus, to prove that something is secure, that is a provable security theorem, even in the presence of a non-uniform adversary, is a better result than only proving it is secure in the presence of a uniform adversary. So if you can prove that an adversary who has access to advice strings can't break your system, that's better than proving that an ordinary adversary can't break your system. Well, you see there's a logical problem here. The logical problem is that the theorem has the form P implies Q. And your adversary is the same adversary for P as for Q. You assume that this adversary, however you're imagining the adversary, you're assuming they cannot solve a certain computational problem, and you're concluding that they cannot break your system. So if you assume a stronger adversary, that means you have a stronger hypothesis and a stronger conclusion. And when you have a stronger hypothesis and a stronger conclusion, your theorem is not stronger. It's not weaker either, it's just incomparable. So there was a kind of fundamental logical error here. And because of that, because of this type of misunderstanding, it actually led Bellari to make a major blunder in a paper that was published in the Proceedings of Crypto 2005. Crypto is the most prestigious annual cryptography conference. This mistake by Bellari went undiscovered for 7 years, and then Alfred Menezes and I noticed it in 2012. If you're interested in details, all of our papers on criticizing the misuse of mathematical proofs in cryptography can be found at anotherlook.ca. Okay, so now, given all the misunderstanding and misuse of theoretical mathematics that occurs not only in cryptography, but in many other areas of science and the non-sciences especially, what is to be done? Well, what can be done about this? I want to give an example of a very small thing that I did just this past term. Now, this is small. It's not a major contribution to anything, and it's not something that Vladimir Lenin would have been impressed by. But I gave a seminar, a small seminar in public writing to our undergraduate students in our university honors program with the title Math That Lies, Communicating Why Some Quantitative Arguments Are Misleading or Bogus. This was a 5-credit seminar for honors program students with enrollment limited to 12. I had 11 students. By public writing, we mean writing that's accessible to the public with clear, brief explanations without jargon, technical words, or acronyms. The setup of the seminar was each week, the students, half of the students were writers, half of the students were editors, were peer editors who would help the writers improve their writing. The students would write a first version that their editor would edit, then they write a second version, and then the seminar would meet, and everybody in the seminar, the 3-hour seminar, everyone would have a chance to comment on all the writing for the week. After that, the assignments were not long. They were between 250 and 1,000 words. After that, I would also send my corrections and comments to each writer, and then they'd write a final version. So it went through really extensive editing and feedback. The students were assigned various readings. Among the case studies I had the students write about, one was David Lee's formula, often called, sometimes called the formula that killed Wall Street in 2008. This, David Lee gave what turned out to be a ridiculously over-optimistic approach to estimating the probability that a large set of loans will default at once. His formula was seized upon by Wall Street to justify its reckless investment practices in so-called collateralized debt obligations, which included packages of large numbers of loans, often home mortgages. And this a reckless practice on Wall Street that involved literally trillions of dollars was what precipitated the financial collapse of 2008. So certainly a good example of the misuse of mathematics. Another example comes from my own university, the Institute for Health Metrics and Evaluation, which became very well known a year ago in the early weeks of the COVID-19 pandemic, because it had super optimistic projections for the total number of US deaths that were likely to occur in the course of the pandemic. They estimated a total, at first, their earliest estimates during the crucial early weeks of the pandemic when people were deciding what should be done, their estimate was 60,000 deaths, which didn't seem so bad because 3 years previously, we had an ordinary flu season that had very close to that number of deaths. So it was an optimistic prediction. Now, in fact, the current number of deaths that have been recorded are around 536,000 deaths, and it's estimated that before this is all over, the deaths will go above 600,000. Disproportionately many in the US compared to the rest of the world. We have around 20% of the world total of COVID deaths, although the US has less than 5% of the world's population. So their estimate using mathematical modeling, in work done largely by applied mathematicians using mathematical models, their estimate was off by a factor of at least 10. Their prediction was seized upon by the Trump administration to justify its refusal to take the pandemic seriously in those crucial first weeks of the pandemic in February and March, or in February and March of last year, or to take appropriate measures. Okay, so my hope is that given this type of background of how quantitative arguments, mathematical modeling, and so on are misused, my hope is that some of the students who take my seminar and other seminars that are being given that are like it about public writing, that these students will become effective writers who can help educate the public and expose quantitative misinformation that gets misused by politicians to advance some ill-considered policies and by commercial interests to scam people. Okay, so that's my hope anyway. I want to conclude with a recommendation of two books, both of them actually written by number theorists that relate to what I'm talking about. One book by Susan Landau, who received her PhD from MIT under the direction of Gary Miller. She wrote a book called People Count, Contact Tracing Apps in Public Health, where she warns about dangers that are likely to result from smartphone applications that implement contact tracing in epidemics like COVID. And these applications use cryptography in essential ways, and they're proposed by cryptographers who did not, for the most part, investigate the human dimensions of what they're proposing. So she, for the first time, wrote a book about all this, about the human dimensions and some of the dangers of unfairness toward the poor, toward racial minorities, and so on. Her book's coming out within a month. Another book, which I strongly recommend, is by Cathie ONeill, who got her PhD from Harvard under the direction of Barry Mazur. She wrote a book called Weapons of Mass Destruction. The title is supposed to be a play on words, supposed to bring to mind the term weapons of mass destruction that was very familiar to us about 20 years ago when the Bush administration was spreading disinformation about Iraq that supposedly had a huge amount of weapons of mass destruction, and the disinformation was used to justify the invasion of Iraq. So anyway, she's using this title to suggest that big data algorithms are dangerous, that the many big data algorithms involve abuses of people and scale up a lot of human fallacies, biases, and so on. And again, that in practice, these sort of mathematical algorithms used in big data science very often result in discrimination against the poor or against racial minorities, types of surveillance that should be unacceptable, and so on. So she gives a lot of detailed examples. Faulty evaluation of teachers. It's especially a big problem in the United States now. There are many really vivid examples of misuse of big data. So that also very much relates to what I've been talking about. Okay, so in conclusion, I want to wish Balu health and happiness on the occasion of his 70th birthday, and thank you for your attention.
Thank you for a very informative talk. Let's clap. Any questions?
Yes, maybe one small question if you...
yes, please go ahead.
Yes, Neal, you mentioned heuristics about polynomial bounds for torsion of ellipticals, uniform polynomial bounds. Isn't it true that known result of Silverman and Andre maybe would tell that the Massor-Osterley conjecture would imply such a bound?
Pardon me, what conjecture?
The Massor-Osterley conjecture, the ABC conjecture.
I don't really know. I haven't kept up with the most recent work on that. So I don't know whether that conjecture implies the conjecture about the polynomial bound. The conjecture about the polynomial bound on Q goes back quite far, I think to the 1980s.
Yeah. Because in my memory, they had a bound which was polynomial, what they call the spiral ratio.
I see, okay. Yeah, you're probably right. I mean, I'm just not familiar with that. Yeah, thank you.
Any other questions? Okay, so maybe I will ask a question. So among the examples that you gave us towards the end, one was about this study from your university about COVID data, which did not turn out to be true. And we saw a lot of such studies and models which went horribly wrong. So do you think, I mean, did COVID-19 modeling pose any unique challenges for which the study of previous epidemic outbreaks did not already provide us with tools?
Well, my impression was that the modeling done by this IHME, the Institute for Health Metrics and Evaluation, suffered from a problem that many of the other models did not. Around the same time, almost exactly the same time in mid-March, there was a model developed by the Imperial College London that predicted 480,000 US deaths. And this model made the front page of the New York Times. It was a model that I believed at the time. They were assuming that the US on a federal level would not take adequate measures, would not take appropriate measures, and they were predicting what that would result with. And of course, that's exactly what happened. The number of deaths is greater than that, but not by at least they have the right order of magnitude. I think the difference is that the IHME model was done primarily by applied mathematicians, essentially using curve fit. They took data from mainly from Wuhan, maybe a little bit from Italy, from the very early time, the very early weeks, and assume that the pandemic would grow exponentially at first, then level off, then decrease exponentially, more or less symmetric way. So they made various assumptions about the type of curve, and then they just fit the data that was available to that curve. Now, what they did not do, for the most part, at that time, later on they improved. Later on they started to develop realistic models, much later when it was too late. But at first, what they did not do was take into account the human side of this. For example, information about mobility of the population, about social customs, things that people are likely to do, events that are likely to become super spreaders, and so on. They just ignored anything related to human behavior and just regarded it as a formal mathematical problem. And so I think this is what the problem was in that case. It's the same problem that there was with the contact tracing apps, that people viewed it as a purely technical problem where you just could almost mechanically apply a mathematical model. That's my understanding of what they did wrong. I don't think it was something special about the COVID pandemic. That probably, if they tried the same thing, the point is they weren't taking into account that American society is very different from Wuhan, and you can't use the shape of the curve. The shape of the curve in Wuhan as of March did look sort of like exponentially increasing for a while, then plateauing, then exponentially decreasing. It did actually look like that. But the curve in the United States does not look like that, largely because of the political and cultural and behavioral differences between and general lack of social discipline in the United States compared to China, which is a very disciplined country when a crisis occurs. So that type of non-science background they did not take into account. That's my understanding of what went wrong.
Thank you. Any other questions or comments? Okay, in that case, let's thank the speaker again.